Okay, so Gina here. All right, so 35 says this. It says a spherical conductor of radius 14. Okay, so here is the conductor. And keep in mind then its radius is 14 because I have a feeling you might be wondering why they put a 14 instead of a 10 in the denominator. That's my common question. Is that true?
Yeah, in fact, all of the parts, the denominator was throwing me off.
Okay. All right. So let me do this. Let me start with a little information from the last chapter. And if you want me to repeat it, I will. But if this makes sense, last chapter, we did some Gauss's law stuff. And we were able to show that if you had a conductor, number one, all the charge would be on the surface. Number two, because it's the same radius, it would be evenly distributed. Number three, it would create an electric field and that on the outside, and that's important, not the inside, but on the outside, the electric field would be the same equation as a point. But on the inside, the electric field would be zero. Are you good with that?
Yeah, that makes sense.
Okay, so that's some result from the past chapter, chapter 24. So as we go into this chapter, and I'll just go right to the definition of the change in potential. Your author says, and it's kind of an interesting, nice argument, that if you're inside, and I'll do that next, that's a harder one. If you're on the outside, you would actually do this integral with this electric field, like a point. And so what you would get, and I'll do the integral if you want, but your author argues that we did this integration early on in the chapter for a point, and since the electric field outside of a sphere is the same as the electric field from a point, you would get the same equation for the potential on the outside as you would for a point. So does that make sense?
Yeah, I'm following you.
Okay. So if you're good with that, I won't actually do the integration, although you can see an integration of 1 over r squared becomes 1 over r. The inside one is usually what throws students off, so that's why I'm trying to get to that part of your question. And here's what's interesting is you would do this integral, if I show you kind of in this picture, that you would start really far away, that would be on the outside, and you'd get closer and 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 closer, and you'd be using this equation until you got to the surface. And so I'm going to put then that the potential on the surface, not inside yet, but just on the surface would be Coulomb's constant times the charge on that sphere times the radius of the sphere. And I'll use a capital R there for the radius. And so that's really kind of where they match, right? The outside, you would just put a capital R right on the boundary. But here's a magical step, if you will. What if then you went inside? Because that's what we have to do. We have to continue this integration from the 14 to the 10. But what is that electric field on the inside? 0. So what you're really saying is I would have to integrate from 14 to 10 the electric field, but the electric field is equal to 0. So what would I get when I integrated 0? No matter how far? 0. So the potential does not change as you move in on the inside of this sphere because the electric field is 0. So the potential on the inside, no matter where you are on the inside, would be the same as on the surface. And so whether they said 10 centimeters or 9 centimeters or 12 centimeters or even at the center at 0 centimeters, the equation for the potential would be this: Coulomb's constant, 9 times 10 to the 9th, times the charge that is on there, which they say is 26 microcoulombs. And then the radius, if you're on the inside, and so they say 10 centimeters and you're on the inside, would be 0.14. And so grabbing my computer here a little bit, grabbing a calculator, I would have 9 times 10 to the 9th, 26 times 10 to the minus 6, and 0.14, 1.67 times 10 to the 1, 2, 3, 4, 5, 6 volts. And maybe I'll switch over here to the solutions. Let's see, let me call up the solutions for chapter 25. Scroll down to 39. Yeah, there it is, 1.67 million electron volts. Yay!
Dr. Young, can you explain one more time the logic for the inside?
Okay, all right. And I'll put a giant circle around this equation, okay? So this equation is saying, how does the potential change? Well, the answer is you integrate the electric field. You add up the electric field. So on the outside, there is an electric field. So on the outside, you would be adding up some kind of an equation, which would be this equation. And of course, if you went all the way to the surface, then this equation on the outside would be R. So this would be the equation on the surface. Are you good with that?
I'm digesting what you said.
Okay. Then I'll say it again, and maybe a little shorter. This right here is the equation on the outside, including the surface. So if I just put the radius of the surface, that would be the potential on the surface.
Okay. Just like my head tries to like memorize things and not understand them. That's like my default like setting, if you will. So I have to go slowly with this stuff.
Sure. Okay. But going back to what I had said earlier, which is really back in a chapter, so I could. That's why I was kind of asking if you want me to redo it. I will. But you integrate this, you get this.
Yeah, I saw that. It's in my notes. That was demonstrated in lecture.
Okay. Yeah. And so now all I'm going to do is say on the surface, your position is capital R. So your voltage or your potential on the surface would be to put in where you are. You are on a position of 14 centimeters. But I think the real key to this problem, and I think what you're asking me to explain again, is then, well, okay, if that's the potential on the surface, I get the 14, but they're asking for inside of it. And what I'm trying to say then is if you continue to do this integral from the surface, 14, to someplace inside, and it really doesn't matter where inside, just anywhere inside. So from 14 to 10 or 14 to 9 or 14 to 0, inside the electric field is 0. So you will get 0 no matter how far you go inside. So that is saying there is no more change in potential. There is no more increase. It's not saying the potential is 0. It is saying the change in potential is 0. So whatever it is on the surface, it remains everywhere inside, because this is how much it would increase from the surface to 10. So from the surface at 14 going in deeper, you would have a change of 0. So whatever it is on the surface, so this is the equation on the surface, would also be the equation for everything on the inside. So I'm going to use the equation for the surface, that's the 14, to figure out what the potential is for anywhere on the inside, whether it be the 10 that they ask about, or whether it be the center of it, or any other thing.
Okay, it's starting to click now.
Okay. Now, with that in mind, let me come back to the rest of the question. The rest of the question then, B, is actually outside. And so it is at 20. So I'm going to come back to this column here and then put in a 20. So this would be Coulomb's constant, 9 times 10 to the 9th. The charge of 26 times 10 to the minus 6. And then the radius, where we actually are. And then this is at a position of 20. And I'll save some room because he says then in C, or maybe I should put this would be A, this would be B, and this would be C. C says then at the surface. And the surface, we can use the equation on the outside because it's right at the boundary. And that's that 14. And then we don't even have to get out our calculator because we argued over here in the hardest one, A, saying that, look, whatever it is at the surface, it's everywhere the same inside. So that's why we used the 14, even though we were looking at the position inside. I'll do the same thing here. If I put the 14, I'd have these same numbers. So I'd get 1.67 megavolts there. This one is different. This is a 20, so I'd have to come back to my calculator here, and I'll just go to re-enter and then just change this to a 20. So I still got the 9 times 10 to the 9th. I still got the 26 times 10 to the minus 6, and then I divide by the 20. And if I go 1, 2, 3, 1, 2, 3, it looks like I get a 1.17 million volts. And I suppose I should flip over and just see what they got. Yeah, 1.17. Now, wait a minute. Did I read it wrong? Because I did potentials, and it asks, the answer has not only potentials, but also electric field. Let me come back here. Calculate the electric field and the electric potential. Okay, my bad. All right, so let me do this. I kind of did it. I just didn't do it explicitly. So A, as we said back here, the electric field on the inside was 0, and the potential on the inside would be the same as everything on the surface. So the two answers for A should have been this: electric field of 0 and a potential of 1.67 megavolts. So that would be A. B, right here, I did the potential and got the 1.17 megavolts. What I didn't do was the electric field. And on the outside, although I did say it up here in this part, that the electric field would be the same as a point on the outside and 0 on the inside. But I didn't actually calculate it. So let me grab my calculator now, and it would be exactly what we just did divided by another 0.2. So this would be 5.85. 1, 2, 3, 4, 5, 6. So times 10 to the 6 newtons per coulomb should be the way to answer part B. And to answer part C, which was right on the surface, the potential, which I did comment was the same as inside. And so that's that 1.67 million volts. And the field on the outside, I didn't actually do. It would be, again, this equation here. Okay, so it'd be this one. And this would be the, well, if I put in the numbers, 9 times 10 to the 9th, would be the 26 times 10 to the negative 6. And it would be the 0.14 squared. So 9 times 10 to the 9th times 26 times 10 to the negative 6, and the 0.14 squared, coming up with 1.19 times 10 to the 1, 2, 3, 4, 5, 6, 7 newtons per coulomb. And let me just flip back over here. So, good. Got the, of course, they wrote it as 11.9 million newtons per coulomb. So, same thing there. All right, yeah, so
they're using they're using the results of Gauss's law for those energy equations.
E is not energy, E is electric field, but yes, it is Gauss's law.
Okay. Yeah.
Okay.
Thanks for the explanation on how the voltage inside is equal to the voltage at the surface.
Yeah. Okay, good. Yeah, let that sink in and come back with any other question you might have. Let's see. Let me go to, I believe Mark was next because he was right before the break and he popped back in here. Yeah. So, Mark, Physics 121 question.
Yeah. So it's the last question of our homework set. I don't know if you've seen it, but it says a bicycle and a car wait at a stoplight. The light turns green at time equals 0. First, the bicycle accelerates at a rate of 2.96 meters per second squared. When it reaches a speed of 8.66 meters per second, it stops accelerating and moves with constant speed.
Okay.
And then it says a car accelerates at a rate of 2.01 meters per second squared until it catches the bike in distance traveled, not speed.
All right. So I think I got the numbers, but I'll probably come back and ask you. But is the question, what position do they meet or something?
Yeah, the question, the question is like, what time does the car pass the bike?
All right. I will tell what time. Okay.
Yeah,
Okay.
time in which, yeah.
All right. Yeah, this is a pretty good question. Pretty. It's got quite a few steps in it. And my advice on a strategy would be, oh, good. This is the same question that Rylan has. Okay, good. Oh, and let me write this down. What's the title of it? Bike car problem?
Velocity versus acceleration in a race.
Velocity versus acceleration in race. So when I add some things to the Zoom recording, I kind of know reference, see if anybody from 121, would care about that one. They could see the recording. And, oh, did I hit record? I think I asked that already.
Yeah, I think it's recording.
Okay. It should, yeah, give me a pause button. Sometimes it's recording. Okay, good. All right. So, okay, back to your question. I would encourage you, when you've got like two things moving, to make two columns and say, okay, here's what's going on with the bike, and here's what's going on with the car.
Okay.
And maybe I'll do the car. It may not be obvious, but the car is a little bit easier to set up the formula because wait, and help me out here. I got the impression that the car just keeps accelerating at 2 and eventually catches the bike.
Exactly.
Okay, so this equation hopefully looks familiar. X equals to the initial x, initial velocity times time, 1/2 acceleration times squared. That look familiar?
Yeah.
All right, so I'm going to apply that equation to this bike and car race. And for a reference, let's say that the position that they start off is at position 0. And I don't know exactly the words here, but didn't it say something about a red light, green light? And so,
yeah.
Okay, so I'm pretty sure that's trying to get you to realize that they're starting from rest. Their initial speed would be 0.
Mm-hmm.
And let me not worry about they, let me just worry about car. So the car is starting with a speed of 0. So if I were to come up with an equation for the position of the car, this would be it. So this is the position of the car. This is the different at given moments in time. Okay, so you good with that?
Yeah, I'm good with that.
Okay, now here, sadly, let's go to the bike. The bike's a little harder because the bike actually has 2 accelerations. See, it says it accelerates at 2.96. So that is more than the car. So the bike is ahead of the car. But here's the catch. The bike gets to this speed, if I wrote it down right, 8.66. And
then it remains. Yeah, and then it remains constant, right, with no acceleration. So what I did was I used the formula twice for each scenario, but I can't get the right answer.
Okay. So you're heading down the right road. Let's keep going. We'll find your mistake here soon, I think. Okay. So the big thing to then remember is that this equation, and I'll just put the same equation for the bike that I did for the car, but here's the special catch. This equation is only valid while you have a constant acceleration. So the bike problem really needs to be set into 2 pieces also. I like to draw a line here and say, okay, this would be the part when the bike is accelerating, and down here will be the parts when the bike is not accelerating. And I think you are already kind of picturing that the car and the bike are going to meet down here. They don't meet up here, because while the bike is accelerating, the bike is always going to be in front of the car because it has a greater acceleration. It's not until the bike gets to some top speed that then the car can begin to get a speed faster than it and eventually catch up. All right, so what I'm going to do is I'm also going to write this same equation for what I'll call part 2 of the bike. And then this is kind of this catch right here. If I really don't really want to do anything unless I have to, and I will have to. But I really don't want to even mess with part 1 of the bike. It's over here, it's part 2 with the bike. This is where the bike and the car meet up. So let me focus on this, but you'll see I can't really answer part 2 of the bike until I do some work back in part 1 of the bike. But what I like to do is start part 2 and see where I get bogged down or stuck, and I'll go to part 1 of the bike. So let's look at part 2 of the bike, and I'll put a plus and a plus, and this is the easy part. This last term would be 0 because on part 2 of the bike, the acceleration is 0. But here's the hard part of this one. What is the position of the bike when the acceleration becomes 0? That can only be answered back here. Now, as long as I'm here, I'll do this one. This says, what is the speed of the bike, the initial speed when the acceleration goes to 0? And that was the 8.66 t. All right. So for me to continue on with part 2 of the bike, let me come back to here. Because now let's talk about part 1 of the bike. And I don't know if I gave myself enough room here. But part 1 of the bike would look like this. Okay, so part 1, the bike would start at position 0, just like the car did. It would start with 0 velocity, okay. It would have an acceleration of 2.96, and I'm not real sure how much time it would have, but that would get it to some position. And so what I'm kind of wondering then is, what is the position here when its speed gets up to 8.66? If I knew that time, I could put it into here and then tell you what position the bike is at when it stopped accelerating and then became 0, and I could put that number right here. So what I'm going to do is write down another equation. V equals V naught plus AT for part 1 of the bike. You see, that's how I'm going to use this speed. In part 1, it starts with 0 speed, has an acceleration of 2.96 for a certain amount of time before it gets to this speed of 8.66. And like I said, sadly, I didn't quite give myself enough room, so I'll squeeze it in here. But if you solve this one for time, grab my calculator, 8.66, and divide it by 2.96, I get 2.93. Sorry, it went over. For the time. And then I can use that back here in this first equation of part 1 to answer what I'm trying to find here. Trying to find what is the position of it when it got to this speed. And now I found this speed. So now I found the time when it got to that speed. I can put that into here and see what its position is. So I've already got the time in my calculator, so I'm just going to hit the square button. Multiply it by the 2.96 for the acceleration. And multiply that by the 1/2. And so this is saying it's a distance of 12.7. So that's what I'm going to put down here, 12.7. Excuse me. So let me just recap. I know there was a lot there for the bike. That's why, like I said, I thought it would be best to write out the equation for the car first. The car is pretty straightforward. All it does is accelerate. We don't have to have a part 1 and part 2 of the bike. And so I'll put in 0 position, 0 velocity, and the acceleration of the car and get that one. But the bike is a little trickier because it has 2 different accelerations. So you got to break our equations down. Our equations are only good for a constant acceleration. So I'm going to do a part 1. And I'm going to use part 1 to figure out where is the position of the bike. And I found it. Where is the position of the bike when it stops accelerating? And that wasn't easy because they did give me the time when it stopped accelerating. They gave me the velocity when it stopped accelerating. So I got to use this equation to say the velocity and solve for the time when it stops accelerating, put it into here, and then that will give me the position. So the bike has gone 12.7 meters by the time it has stopped accelerating. So that is what I'm going to put down here. So in part 2 of the bike, I'm going to think of it this way. In part 2 of the bike, I can say that when the bike has stopped accelerating, it is at a position of 12.7, has a speed of 8.66, and now the acceleration is 0. And so that means in part 2 of the bike, when the bike has no longer accelerated, this is the equation for the position. Does that make sense?
Yeah, totally.
Okay. Now, sadly, it even gets a little bit harder, but we're almost there because this is where a line I like to use a lot. Make sure you're reading the math. You know, that's how I knew to come back up here to get this. But let's look closely at this time. In part 2, this is the time after it has reached its acceleration. So in other words, watch this. If I put in time equals to 0 right here, time equal to 0, I would say the bike is at a position of 12.0. So in part 2, this time is the time after. Did you catch that? After it has stopped accelerating. This is not the time from when the light turns green. Now here's what I'm going to ask you to go back and give me the question. What's the question?
The question is, the car accelerates at a rate of 2.01 until it catches the bike in distance traveled, not in speed, which happens at time t. So we're just solving for that time that it passes.
But okay, I think and here's what I'm trying to be extra careful, is the time they want when they catch it is the time measured from when the light turned green. So they don't want this time. This is not the one they want. This is the time.
So they want that one.
Yeah, so I'm going to do one more step here. This is 12.7 plus 8.66. And if we want our time to be measured from when the bike has stopped accelerating, I'm sorry, let me say that a little better. This time is the time after the bike has stopped accelerating. But if I want my time to be the time from when the light turned green, then I need to subtract from it the 2.93. Let me say it this way. Let's say the bike has been riding for 3 seconds. It reached its top speed just a moment ago. So you would want to take 3 and subtract the time it took to get to that speed. That is how much time it has been beyond, or since it has reached an acceleration of 0. I see a blank stare.
No, I'm just, that's the one, I got all the way down to that point, but I didn't think to do the T minus, but I get why.
Oh, good, you get why, good.
Yeah, I get why. I was just thinking we add up all 3 of the equations and have the 2 bikes equal the car, but that doesn't give me, it gives me like a negative number, so.
Yeah, I think that's where you run into a trouble. It's easy to mess up the meaning of this time.
Yeah, cool. All right.
So then, and maybe it sounds like this isn't an issue for you, but for anybody else watching it or later on the video, let me then say that they want to know both the position and the time when they meet, right?
Yeah.
So since this is the equation for the bike, the 12.7 plus 8.66 t minus 2.93, and this is the equation for the car's position. When you set them equal to each other, what you are saying is, when does the position of the bike over here match and equal the position of the car?
Yeah.
And then solve for t.
Yep.
Now, I would say that also, this is not the only way. I'm not even sure it's the easiest way. It's just kind of the way that I was thinking. And so there's other sets of equations that could be used here. But I think the real hard part about this, in fact, I would say this about one-dimensional motion. One-dimensional motion is actually pretty easy if you have one object with one acceleration.
Yeah.
Because all of our equations are about one object with one acceleration. Where they get hard is if you have 2 objects, because now you have to apply those same equations to the 2 objects and you got to keep them straight. And it gets double hard when they have different accelerations, because you got to apply the same equations at different parts. So I call it part 1 and part 2 of the bike. This could have even been extra hard if the car also had two different accelerations. But
Yeah, I can see.
but these are hard because you have to be organized and know what the meaning is. And that's why I think a chart separating the two objects and then some vertical or some horizontal lines separating part one and part two are kind of nice, especially as you get into part two, which is measuring time from part two, but you want to compare it to something else, which is measuring time from part one. And so you got to connect the time in part two with the time in part one.
Yeah, it makes sense. Thanks a lot.
Yeah, so that's a hard one. I think you said this was the last one on the problem set?
Yeah, that's the last one on the homework.
Yeah, makes sense. So save the last one, the hard one, for the last.
So does that end up with the quadratic formula to solve it?
Yeah. Should I continue to solve it?
I mean, I have different numbers than you anyways, because the computer gave me different numbers, so I'm trying to solve it myself. But I think I put my numbers in as you were going along. But
All right. Well, if I do 12.7 plus, and then this would be 8.66 t, and distributive here would be 8.66 times 2.93. So that's a 25.4. And then to write this in the usual quadratic form, I'll leave the quadratic on this side and put the what we call the linear term over here. And if I combine these two, the 12.7 and subtract the 25.4, and then move it to the other side, so now it becomes plus 12.7. I can solve for a time, and it would be the opposite of b, so 8.66 plus or minus. We're going to have to think a little bit because our math's going to give us two answers, and one of them is going to be bogus, so we got to think about which one is a bogus answer. More on that in a second. B squared would be 8.66 squared minus 4.
sorry, is there a step in there? Shouldn't you have at some point combined that 12.7 and that negative 25.4?
I did.
did.
Oh,
And interesting.
It became
Yeah,
12.7?
Yeah.
Okay.
It just happens to be twice that.
Okay, cool.
Yeah.
Cool.
Yeah, that was coincidental, could throw you off.
Okay, cool. I see what's going on then.
Yeah. So then, let's see. So minus 4 times A times C all over 2A. And so, maybe I'll break this into one more step. I double this, that's 2.01, okay? But this is the one that I want to be careful with what goes in this square root. So this is 8.66 squared minus 4 times A, 1.005, times C, 12.7, and then the square root of that. So this is 4.89. So there's two answers here. And like I said, one of them's bogus, but we probably better think about which one's going to be bogus. And maybe bogus is the wrong word. Maybe I should say one of them is not the one they want. It's not really bogus. Well, maybe we should talk about it. But the first one, I'll do the plus sign. So this would be 8.66 plus 4.89. So I add them and divide by 2.01. So that would be the 6.74 seconds. The other one would be the 8.66 minus 4.89 and divide that by 2.01 and get a 1.87. And I don't know, maybe bogus wasn't such a bad word because we know, coming back to this earlier part, that the time that they meet has to be greater than 3 seconds or 2.93. So we know this is not it. Hope I did that right. This was a tough one.
Yeah, that's it. Thank you.
Yeah. And we could, probably not worth it, but we could try to interpret what that would mean. But I think it's suffice to say that it's bogus because it's a number that didn't fit our parameter. It's what in Matthew would call an extraneous root. It's what shows up as you're trying to solve it. And there's kind of a meaning to it, but it's a meaning that doesn't match our problem. So I'm just going to throw that out. Yeah. Sadly, though, it's a little hard, maybe a little hard to see. I don't know. Sometimes we get a plus and a minus, and that's kind of what I was hoping for. A lot of times it'll be a plus and a minus, and you can go, well, it can't be the minus one because it started at 0, and then the minus must be bogus. But this one doesn't have a minus. We can't say it's bogus because it's minus, but we can say it's bogus because it doesn't fit a parameter that we defined earlier, that the time has to be in part 2. It has to be greater than 2.93. Oh, good. And you said this checked out on the computer, so I did it right? Good.
Yeah.
All right. Thanks.
And thanks for sending me that link to the tutoring yesterday too. That was really helpful.
Oh, good. Yeah. And again, apologize. We're just, yeah, a little just foul up on people learning this whole new online Zoom and how to put a link on a web page, and it just didn't work, but we got it straightened out.
All right, cool.
Right. All right. So as you're back to the chat, okay. So that 2 of you had that one. Okay, that's good. I have a question, Ashley here regarding the upcoming test. Oh, yeah. Go ahead. Are you still on? I don't see you.
I think she might have left.
Yeah, maybe she'll just send me an email or pop back in.
Okay. I actually have a question on chapter 2. I'm in your 160 class.
Oh yeah. Go ahead, Kevin.
Let's see here. Where's chapter 2? Oh wait, no. Wrong one. About number 29.
Okay, so chapter 2, number 29. Let me also write this down. Chapter 2, number 29. Let me click over here to chapter 2, number 29. Now, this class has conceptual and exercise. Are these conceptual or exercise?
This is the conceptual question.
Oh, I think I'm gonna need to apologize. I think there's a typo in the solution manual.
Really?
By throwing you off. Let me just read it here. It says, assume that you have an airplane accelerating from 550 miles per hour to 550. And I think this is what you did. You said that the acceleration is change in velocity over time. And so it's not the amount of velocity, it's the change.
Oh, okay. I got confused with both with the concept right there.
Okay, so you need to subtract these two. 555 minus 550.
Oh, okay. So then it'll just be 5.
Yeah. Now, but let me keep going. Let me because I think there really is a typo in the solution here that'll also that I'll hopefully catch, so that won't throw you off. Because now let's go to the car. So the car says it accelerates from 50 miles an hour up to 59. So again, acceleration is change in velocity divided by time. And so the change here would be a 9.
Cash money.
Hey, Brother Mon.
How you doing?
How you doing? I'm good, man. Just about to go.
Sorry, give me just a sec.
Okay, I'll mute you.
No worries.
Okay. All right. You still with me, Kevin?
Yeah, I'm still with you.
Okay. All right. So the car, I would put at 9. It has a change of 9. And I want to say the same thing, that it sounded like a light bulb went off for you, that the numerator here is not the speed, it's the change in speed. So the car actually has a greater change in speed than the airplane.
Airplane. Is it because of mass or?
Well, right, going into the next chapter, we will see that the acceleration is a combination of the force and the mass.
Okay.
And the mass is in the bottom. So you might say, yeah, it's easier to make a car accelerate than an airplane because there's less mass to a car. However, you don't want to say that too quickly, because the other factor of acceleration is the force. And an airplane has bigger engines too.
Mm-hmm.
So the acceleration of an airplane, like on takeoff, is pretty significant. Even though it's got a lot of mass, it's got a lot of force from the engine, usually 2 engines or something.
Yeah.
Yeah. So we're not real sure why the car has a greater acceleration in this problem. We just know that it does based on the numbers they gave us.
Yeah.
It could be because it has a force, a big force, or it could be because it has a small mass.
That's probably it.
Yeah, that's why motorcycles are really fun to ride, because
They're
even though their engine's not very big. You know, you take like my Honda 250, it doesn't have much of a force compared to my car, but it's really light compared to my car.
Mm-hmm. That's why motorcycles are the second, if not the fastest vehicle in the world.
Okay, now those 2 ways of saying that. It's why they can be the most accelerating object as well as the fastest. Because again, acceleration is change in their speed.
Mm-hmm.
So 0 to 60, and I wouldn't call 60 fast, but 0 to 60 is a short amount of time. It's got a huge acceleration.
Mm-hmm.
And then depending on the gearing, you're right. The gearing, you could get really, really fast. Mine can't. So, like, I wouldn't say my motorcycle can go faster than a race car, but I can out accelerate a race car.
Mm-hmm.
So if we're just racing across the intersection, oh yeah, I can take it. Yeah, it's same thing with braking. I can brake, which is why you can get a little careless on a motorcycle and get right up on somebody's bumper.
Mm-hmm.
If they fully brake on a car, you can out accelerate them down to a stop. As long as you don't hit them at first, as long as you have enough reaction time to put on the brakes, you will stop much, much quicker than they will, even if they locked it up. Yeah. So that motorcycles in general aren't safe, but one thing that makes them a little safer
is a versatility.
Stop quick. You can take, if there's danger, you can accelerate out of the danger. Yeah. All right. So forgive me, I got a little sidetracked there. Let me come back to the problem. What was the third object?
The bicycle.
Bike. Okay, so the bike, the same idea. The bike says you start at a 0 speed and
Oh, it's a 9 speed, I think, or 8?
8 miles per hour. So again, the change in the speed would be an 8.
Okay.
Now, the other real important part of this is right here. It says if all 3 vehicles accomplish this in the same amount of time. So this number in the denominator is the same. Which one has the largest? Well, it must be this one, because it would be 9 divided by some number, which would always be bigger than 5 divided by that same number, or 8 divided by that same
Mm-hmm.
number. And so the car should win. And I'm going to just jump over to the solutions here.
I actually forgot there was a solutions page.
Oh, yeah, okay, well, good. Well, I'm glad I'm mentioning that, because
Is it the very last?
that can be helpful. It's do you have the solution page? No, I have it posted on our server. If you want, I'll put it in the chat, but if you want, send me an email and I can send it to you in just a second here. But I'm going to go down to 29 and see what they say. No, is it 29? Oh, I'm in the wrong chapter. That's why I'm in chapter 3. Okay. Somebody, you're asking about chapter 2.
Yep.
Okay, so 29 says the car. Oh, good. There's not a typo.
Oh,
Great.
okay.
I thought there was a typo. Oh, good. So I'm sorry about misleading you that there's a typo, but let me do this. Let me copy this link here. Come back over to the Zoom. Let me go to the chats. If I can find the Zoom in the chat. Let me paste it, and there it is. If you want the link there. And then
Oh, okay.
like I said, it's you can do it by email, or if you go back to, that was on the welcoming email I sent.
Oh, okay.
And so there was a
Oh,
bunch
yeah,
of,
it is. I must have misread that.
yeah, there was like 4 things in that welcoming email. There was the textbook, but this was one of them.
Huh.
Help?
Okay, yeah, I see it.
Yeah.
Is it on the first week assignments, I think?
Oh yeah, and it's repeated on the first week assignments. Give me a second here. My dog's going crazy here. I'll be right back.
Yeah.
All right, thank you. I'm back here. All right, Kevin, we good?
Yeah. Yeah, thank you very much.
Uh-huh. Let me see. Question about the upcoming test. Did Ashley come back? No? Okay.
Yeah, she didn't come back.
Okay. And you got another question, Kevin, or anybody else?
Actually is also, this one's on, let's see. If I can find it. On the exercises for chapter 3.
Okay.
It's on which one was it again? Trying to find it through here. Oh, okay. It's number one actually. It's number one on exercises.
Okay, so number one, let me get a clean piece of paper here. All right, so chapter 3, number 1, and it says this. It says, find the size of the net force produced by a 6 Newton and an 8 Newton each in the following arrangement. Okay, now the A says that the two forces act in the same direction. So one of the things that I hope you're starting to get out of the lectures is that real important to physics is not just the number. I think you would agree that, 8 is more than 6. But also,
It's the unit, right? It's also the unit in the direction.
oh, yeah, and the unit is important too, right? So there would be a difference between 8 meters and 8 centimeters, yeah.
Mm-hmm.
But another big thing is the direction.
Yeah.
So if I were to draw a picture of what I would describe B, I would say these two people are pushing in the same direction. But in B, they say they push opposite. So this would draw a picture look like this. Somebody pushing with 8 to the right and somebody else pushing with, 6 to the right and somebody else pushing with 8 to the left.
Mm.
And
Okay.
see, in both cases, there is a 6 and an 8, but you don't get the same thing. You see, these two are in the same direction, so we would add them together. We would say the equivalent of those two, the 6 and the 8, come out to be a 14.
Mm-hmm.
And so even though there's two people, we can kind of think of that as one person pushing with a 14. And we need that because Newton's second law, which I had brought up in that past problem,
Yeah.
you want to know what the equivalent force is. We call it the net force. So if there's more than one force, you've got to put them together and say, well, what are those two equivalent to?
Mm-hmm.
So in a problem like this, I would have to say these two are equivalent to one person pushing with a 14.
Okay, so yeah, so the net force, of course, is the sum or like of
Yeah, it's probably best not to say the sum.
Oh
it's
yeah,
the combination.
Combination there.
Yeah, because look at B, and I'm hoping the picture helps. See how they're fighting with each other? One person is pushing to the right and the other one to the left.
Yeah.
So I would say the net force, the combination, is the difference. That's why I don't want to use the sum of them. It's the combination of the two.
Okay.
And when you combine them, you have to include direction. So sometimes we add and sometimes we subtract.
Mm-hmm.
And that's what this problem is trying to get at.
Oh, okay. So, yeah, and then of course at the angle for the angling of each other, does that are they adding or are they subtracting?
Now this one's a little harder. Now let me use that same word. I'm not going to say add the forces together. I'm going to say combined the forces.
Okay.
Right? And if drawing a picture really helps, because back in A, when I drew a picture like this, I go, oh, well, they're together. That's adding. Here, they're fighting each other. That's the difference. So I subtracted. In this picture, I'm making a triangle. And then I need to remember what we called Pythagorean's theorem.
Oh, okay.
Mm-hmm. That if you know the legs of the triangle, so there it is, I know the A and the B, I can find the hypotenuse.
Mm-hmm.
And so I wouldn't say I'm either adding them or subtracting them. I'm using Pythagorean's theorem to find it.
Mm-hmm.
So in this case, it would be a 6 squared plus an 8 squared is equal to c squared, which I guess is 36 plus 64, which is 100. And so taking the square root to finish it,
That'd be 10.
would be a 10, right?
Okay.
So all of these, and this is the whole point, is that the two forces are the same in all three scenarios, but the combination of them is not. This is a 14, this is a 2, and this is a 10.
Mm-hmm. There, yeah, that really helps a lot actually, because like
Good.
it was mostly just having trouble. Like it was mostly just me getting confused with C, because like I thought it was like multiple. It's technically multiple, you know, but it's more Pythagorean theorem.
Yeah, yeah. Good.
All right, thank you very much.
All right, you bet. Let me come back to the chat. Oh, so it looks like I was the last one in the chat with the solutions for you. So make sure you get that, Kevin.
All right, thank you, thank you. Have a good day. Have a good day, doctor.
Ah, you too. Take care.
I had a physics 123 question.
123. Okay, shoot.
Yeah, let me start my video. So it's question 8. I don't know if you have it in front of you.
What chapter?
It's from chapter 25.
25. Okay. I do have it. Let me, I'll call it up here. Chapter 20, I'm sorry, 25. Okay, number
number 8, yeah.
Oh, yeah, I see this one. Okay, good.
So they got like a charge on a string and an electric field along the x-axis.
Okay, so let me write here 25, number 8. And let me kind of repeat here as I get started with something I hope you saw in the video lecture.
Mm-hmm.
That in this chapter, we're learning to work with electric potentials.
Yep.
And the reason why is that can lead to energy. And because of conservation of energy, so I'll just put conservation of energy, that can lead to kinetic energy, which leads to speed.
Right.
All right, so that's the approach. And so that was kind of a refresher from physics 121 and saying, okay,
Yep.
what did we do in 121? Okay, so with that in mind, I'll get myself a new piece of paper here and draw what they have. They have what looks like a horizontal line out to point A with an electric field pointing along that x-axis.
Mm-hmm.
And then they have a charge Q, a distance L, and an angle theta. And I'll mention the forces, but this is best done with energy. The forces would be pushing it this way and would make it swing down to here. And it would probably go too far, slow down, and go back and forth.
Right.
So they kind of look like a pendulum on its side. You know,
Yeah.
yeah.
Oscillation kind of.
Yeah, exactly. And coming back to this diagram I was showing here, I think the harder part is this, because as you'll see, going from this to energy is really easy, and this is really easy, and this is what we did in 121. So,
Mhm.
so the big step, I think, is here, but we'll see.
Okay.
And so if I read the problem here, they say that the particle has a charge of 2 microcoulombs. It has a mass of 0.01 kilograms. The
Yep.
string has a length of 1.5 meters. And what did it say? The particle of the string pivot along a line of friction horizontal table. The particle is released from rest. Okay, so initial speed is 0. When this is at 60 degrees,
Yep.
a uniform electric field of 300 volts per meter determine the speed. Okay, so I'm going to start by saying, what is the change in potential?
Right.
So the object actually moves kind of along an arc. And so that means it has both an X and Y motion. So technically, this is actually 2 pieces to the integral, taking you back to dot products. If you remember, A dot B, you would put the X components together and then add that to the Y components.
Okay.
So that's what I'm doing here. I'm saying that, okay, this thing's going to move in the XY plane. So in other words, there's a movement on the X. And so I would want the X component of the electric field when I do that integral. And then here would be a movement in the Y direction, and I would want the Y component of the electric field. So I'm going to put those 2 in. So the magnitude of the X component of the electric field is the 300. And what makes this look like it was hard at first, but now becomes easy, the electric field in the Y direction is 0. They said the electric field was only in the X direction.
Okay, right. So you can get rid of that.
Yeah, so this integral, I'll just put plus 0, no longer depends on what it does up and down. It only depends on the X.
Yeah.
So maybe putting in my limits, I would say, okay, where does it start? Well, it would start at 1.5 cosine of 60 degrees. And when it comes all the way down, it will now be at position 1.5. So 1.5 cosine 60 to 1.5. Unfortunately, they were nice to me. I don't even have to get my calculator since cosine 60 is one of those special ones. It's a half.
Yeah.
So this would be 0.75 to 1.5, 300. They were also extra nice to me in the sense that this is a constant. I can just pull it out, and so that's just X evaluated from 0.75 to 1.5.
Yeah.
So that's minus 300, and 1.5 minus 0.75 is also a 0.75. All right, so now I'll grab my calculator. So negative 300 times 0.75 gives me a negative 225 volts. So there's the change in potential.
Right. Now
Alright,
you
so
need to
now-
solve for the potential energy, or
Yeah, so and let me keep going, but I think that was the hard part. I hope
that
anyway.
was. Yeah, because I didn't think to split the electric
Oh.
field into X and Y. That was the main issue.
Ah,
And so I was sort of stuck at the beginning of the problem because of that. But that makes sense now,
okay,
obviously.
all right. So should I leave it there or keep going?
I mean, I just assume you're going to multiply by the charge to get the.
Right. So yeah.
I sort of know it's.
So the change in potential energy would be the charge times the change in potential. So the charge is the 2 times 10 to the minus 6th. The change in potential is the minus 225.
Right.
So times 2 times 10 to the negative 6. So that's a decrease in potential energy of 4.5 times 10 to the minus 4 joules.
And it's a decrease because it moved along the electric field in the X, I guess.
Yeah, there's a lot of ways we can say that. But the potential always decreases if you come back here to this math when you move in the direction of the field.
Right.
So anything that goes this way would be a decrease, and that's what we got. We got a decrease of 225 volts.
Okay.
And of course, in the other direction would be positive. And I'm just kind of curious where this goes myself. So I'm going to put here the change in kinetic energy would be 1/2 mv final squared minus 1/2 mv initial squared, but the initial is 0. And the change in potential energy was that negative 4.5 times 10 to the negative 4 joules. The mass was at 0.01. Let me just double check that. Yeah. So if I grab my calculator, there's oh, I messed up. It's negative of a negative. So there's 2 negatives here.
Yeah.
The negative of the negative. So that's a positive number. So let me just change it to a positive. Okay. Then if I go times 2, and if I divide by 0.01, and then if I take the square root of that, 0.3 meters per second, then is the speed.
All right. Thank you.
Ah,
I got a good understanding of it now. All right.
very nice. You bet. All right, I'll come back over here to the chat room. All right, so looks like a Max popped in here. I don't know if you had a question, Max. Nothing in the chat room. Why these taking a break or
I
something?
did. Should I post?
No, just go ahead and say it.
Go ahead. Ooh, 1 second. My internet is a little slow. Okay, I think I'm good. I had a question on number 60 on chapter 25.
Okay, so 25, number 60. All right, let me write that down. All places here. So number or chapter 25, number 60. Let me come over here to these questions. Oh, okay, yeah. We did this a little earlier. We'll do it. Oh, did we do it? Yeah, we did it back at 10 o'clock here, but I'm gonna do it again here for you. because it says here.
If you already did it, I can review.
Well, I have you now, and
Okay.
everybody's bugging out. It's getting late here. Yeah, we've only got about 7 minutes, so I think yeah. Let me just do it. It might be nice
Okay,
to
sounds good.
see it,
Let's do it.
and then you can also review this one or the 10 o'clock one. I'll post that both of them later tonight.
Perfect.
But here
Okay.
it says, and it looks like this, where you have this rod here on the x-axis that has a charge density of lambda. And they say the rod has a length L and it's a distance A. And then there's this point P up on the y-axis at a height of B. And they say, go ahead and find an expression for the potential there. All right, so maybe I'll change colors here for a second and just say, imagine just not the whole rod, but a little chunk somewhere in that rod that has a charge of dq. Because the key to this problem, and many like it, are this, that the total potential can be found by adding the potential of the individual pieces. And so this is where we start using our calculus. This integration sign really does mean a summation of a bunch of little things. So taking this integral, I would be asking then, what is the potential from this little piece, and then the one next to it, and 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 add them all up. That would give me the total potential at point P from all these charges down here that are creating that potential. And so I'm going to jump back to the beginning part of this chapter. I don't think they're asking you to derive the potential from a single point. But at the beginning of the chapter, we did derive what is the potential from a single point. And so if we take a microscopically small point and call it Q or dq, then that's the charge at that point, and the distance away, r, is this distance here. So that's what I need to do, is to integrate this. This is the potential from that point, and then the one next to it, the one next to it, and the one next to it, and the one next to it. And each one, of course, the r gets a little bigger as I go to my right and a little smaller as I go to my left.
Right, okay, yeah.
Okay. So that's kind of the conceptual / math part of it. But now, to make it a doable math problem, we have to change each of these into, an x, so we can actually go from the beginning of the rod here, which I would say, x equals a, to the end of the rod, which would be x equal to a plus L.
Mm-hmm.
So that's where this charge density comes into play. And we did it quite a few times in the last chapter, that you can say that the charge density is a little charge over that little length, but that little length is the dx, and so move to the other side, you have dq equals to lambda dx, and that's what I will put there then, lambda dx. So that's an important step after we go from the physics of it to the math. We actually really need a dx, and so we needed that step to switch that into a dx.
Mm-hmm. Mm-hmm.
And then also hard in here, or at least what's going to make the integral hard, is that this r depends where you are on the x-axis.
Right.
So if we were adding up chunks and we were saying we're looking at a chunk that's a distance x, and of course we're up a height b, we can get r using Pythagorean's theorem, because r squared would be a b squared plus an x squared.
Right.
So b squared plus x squared. Of course, then we have to take square roots to get just r.
Yeah, gotcha.
You know, a lot of problems last chapter, since we were dealing with electric fields, had r squared, so we didn't have to do that. But for this one, it does, which makes it a pretty hard integral.
Yeah, I think I ran into something where it was one of the natural log integrals, which I had completely forgotten how to do. So.
Okay, good. And I want to say something about that here in a second. So my limits then would be from my first little chunk of charge at A,
Mm-hmm.
and I would then add it to, and keep adding until I got to the end. And so that would be the limits of my integral. Now we can actually get into the calculus, and I want to point out, I'll even change the order of the plus sign just to make it match what I want to show you. But when you have hard integrals like this, and when I say hard, they're not the simple power functions or they're not the u sub. Those are kind of easy to recognize. This is probably well, it kind of looks like a trig sub, but it also kind of looks like a partial fraction. But here's what I want to say. And I'm going to switch my camera now and go to the textbook. The tests are going to be open book, and you can then switch.
What? I guess you linked the online survey version. I have the OpenStack, so does OpenStack have something similar, or should I just look at the online survey version?
Oh, let's take a look for a moment here. Yeah, maybe you heard me say it in some of the other videos.
Yeah, I remember.
Let me just write it down. So I'm at the survey book right now.
Mm-hmm.
Maybe I should see. Can you see that on your screen? Yeah, good.
Yeah, I can see.
Right, and so let me find the one we are trying to pinpoint. I think it's this one right here. Yeah.
Yeah. Yeah, this one came up earlier as well, but I couldn't find it. I had to look up the.
Yeah, so feel free to look it up anywhere. You could use
I used like Wolfram Alpha to just integrate it, but.
Yeah, and that, you know, because we live in kind of this information age, that's kind of been the.
Yeah, but this section in the textbook is I'll definitely use this. I forgot about this.
Yeah, and I was just going to, I don't know if it would matter to you, but I am kind of curious by myself. If I go to the OpenStack book and scroll to the back, what does it say there? Scroll. Thought I saw an appendices that said math. Now, Appendix E does have math formulas. Okay. And so here's the trig ones, trig identities, binomial expansion. Well, now they got derivatives. So here's some integrals. Of it. I believe that's the same thing. That's.
Yeah, I think there it is at yeah.
That's interesting. pretty sure I've gone through this before and proved to myself that that's the same thing. Yeah, because it's an inverse sinh, and you got to remember a sinh function is exp. So the inverse of a exponential would be a natural log. So I'm quite sure that's the same thing, but I don't care for it written in that form. I like it written in.
It's a little confusing.
Okay, so well, with that in mind, then let me come back to my share screen, and I'll jump back over to my camera here. And I got to turn on my screen share, my phone, and it's trying to catch. Here we go. All right. So I wrote down the integral we just saw.
Yep.
And then it would be evaluated from a to a plus L. Oh, and it looks like my screen got a little hiccup in it. It's about 7 seconds behind me. So, well, we're kind of at the end of our time, so I won't reset it. But I'll write it out, and maybe you're even good. This would be.
Yeah, the setup was I think the thing that was catching me, but that makes a lot of sense. Chopping it up. I mean, same process we've been doing. It's just sometimes hard to see, I guess.
Okay. Well, and if you want, I'll call it good here for the day. But if you want, you could go back to when I send this out, the Zoom chat. It's the first example I did at 10 o'clock. So, but I went through the math in complete detail, and because when you first put in the math, it doesn't look like it's gonna come out to be the same solution in the solution guide, but after you manipulate around for a while, it eventually does.
Okay, I'll take a look. Yeah, thanks for your help.
All right, looks like you're the last one here. So I'll say, have a good day. Keep working on these and send questions.
All righty. Thank you very much.
All right, bye now.
Bye.